Did you all get those? All right. I had something weird happen. Well, it's actually happened for a while. When I try to boot up my laptop, if it's in a docking station, it won't boot. It'll just stay there. It's a Lenovo Yoga 12. It's a ThinkPad, and I don't know what in the world the problem is. I want to talk about this because some people did have a very poor understanding of this. And I want to make sure with Smith charts that everybody clearly understands. You're going to be getting more questions about Smith charts in the future, and you have to be really familiar with them. Let me go ahead and share this screen, because we're going to move on from here. Now, can you all see right here? This is what I've sent you. I think, I'm not sure if it was it's Saturday, right? I sent you this on Saturday, I think. Where these are the answers, but frankly, what I try to do is get something that would be meaningful to you. So for the first one, I mean, if you have this is the best I can do for something that I can render here without actually having to draw and use a document cam. Can you all see this Smith chart right here, class? All right. Now, this is the first problem where we're going to use a capacitor in parallel, right? Everybody? Now, a capacitor has a reactance of minus J over omega C. Do you all agree with that? That means it has an admittance. Since we're in parallel, we're going to be using admittance. Oh, we'll normalize it first. So it would be minus J over omega C Z naught. Correct, class? That would be the normalized impedance, right? Now when we get an admittance, it would be plus J omega naught C Z naught would be the admittance. You notice it's plus J, correct, class? That means when we start, we say here's ZL right here where the red dot is. Do everybody see this? This is 0.3 plus J 0.5. This is the quiz. Do you all agree with this? Let me see if I can spread this out so I can actually see it. And if you don't mind, turn your cameras on. I appreciate if you do that, because that way I can see you and I can tell if there is a terrible misunderstanding. It really does help me. I understand some people don't want to probably show themselves unless they're dressed appropriately, but it helps me. So follow me on this. Here's where you come in. This is Z. Hold on, I got a question. I don't have a camera. Okay. If you can get in a camera for next time, I'd appreciate it, because now on exams, you're going to have a camera. I can't give you credit for it. So anyway, here, this is 0.3 plus J 0.5. Now, if you have a Smith chart, you can find this, but I think everybody understands that. Correct, class? Now, the next thing, I go to the admittance domain. That's this point right here. That's 1 over ZL. It's at the conjugate point, exactly 180 degrees around a circle of radius, where you really just plot go from the center of the circle to the point ZL and just make a circle. Now, I have to move here. And the first point I'm going to hit is right here. Now that's 1 plus J something, correct, class? 1.J 1.57. That's a plus J. If we had a capacitor in parallel, it can never get rid of it. Do you agree with that, class? All right. We have to move to this point, which is almost around the circle entirely. We have to move to the point where we get 1 minus J that. Everybody got that? Because we're going to be adding a capacitor in admittance domain. And this is going to be about, I believe it's 1 minus J 1.57056. The distance you move is right here. It's 0.4934 lambda. You all see this, class? And that's literally from here, the mile marker here to the mile marker here. You take this mile marker and subtract this one from it. Pardon me. You're going to take this mile marker and subtract this one from it, and then add 0.5 lambda. And you end up with that right here, 0.4934 lambda. Now, that's how far you go. And next, you have to design a capacitor that will get rid of this J 1.57056. Correct, class? All right, that means 1.5, I think it's up here. this right here, 1.57056, has to be equal to j omega c z naught, correct? And therefore, to find c, we simply take 1.57056 and divide it by 2 pi, which is omega z naught, and we get this capacitance here. Do y'all agree with that? All right, now, I don't know how many people, but a bunch got it right completely. But I want to make sure you don't make this mistake of going to this point, because there's no capacitance you can add in parallel that will get rid of a positive J. Follow me? You got to go to the other point. That was the big thing about this problem. Now, we use the same exact transmission line. Now we do stub tuning. I didn't specify which one I wanted shortest, so it didn't matter which conjugate point I went to. Remember, it's a shunt, so it's in the admittance domain. Correct, class? So we come in here, we go to this point just as before, but now we can go to this point. That's legal, right? Because we're going to have a stub we're going to add. And at this point, I get 1 plus j, 1.57. The distance I move is 0.39 or 3494. So I move from here to here, and you could take this point, subtract this point from it, and add 0.5. And then I still have that j 1.57, right? That's a positive j 1.57, correct, class? Now here's where it becomes important you see this. When I have a stub, and this is a short circuit stub. If it's a short circuit stub, the impedance is 0. The admittance is infinite, correct? And where we go on a Smith chart to deal with the length for that would be here. That's where we start. That's the point infinity, correct, class? Now we have to move down and make sure you can see this until you can see right here coming in perpendicular, a line that says 1.56 roughly. Can you all see that? Take a Smith chart and make sure you can see this, because I think some people didn't have an idea where to go with this one. You should see right there is about 1.57. Then you draw a line straight through that point out to the edge, and you're going to read a mile marker there. And actually, I've got this over here, I think. About 0.344, 0.342, about in that range. And you'll subtract off 0.025 to get the distance. And the distance of the stub is right here. If you can see this, can you all see the cursor on the screen right here? Right? It's 0.0902 lambda. That's exact. And so that would be the length of the stub. So these are the answers. And were there any questions about this at all? Okay, and if you had trouble, make sure you figure out what the problem is, because here's the typical questions that come next time. Suppose I wanted to do the same problem with an inductor in series, right? For the first part, how would you do that? How would you do it with a capacitor in series? How would you do that same problem with an inductor in parallel? So you can see the permutations. Now with a stub, there's only one thing I can do. Actually, two things. I could make it an open circuit stub, or I could have the stub be connected in series. And these are the variations that can happen for Smith chart stub tuning. And that's it. It's either with an element, an inductor or capacitor in parallel or series, or a stub in parallel or series. Make sure you can do all variations, because that's the type of stuff you're going to have to be clear about in your head. Remember, yeah.
Is this the kind of question that we would see on a test?
Absolutely, absolutely. Matter of fact, I'm guaranteed it'll be something like I just said. It'll be one of those combinations. And I may ask you to minimize the length of the stub or the length of the through line, one of the two. But if you're familiar with this, you won't have any trouble. Now, I'll tell you, historically, what I've seen is people that go and do a whole bunch of Smith chart problems, not just the ones I assign. I believe this will bear out. If you go ahead and take a look at Wentworth's book, but just go on the internet, and there's cajillions of Smith chart problems. Go through and do a whole bunch, like 15 of them, and go. They'll talk about every possibility. They're going to say you want how far from the load is the first voltage maximum, how far is the first voltage minimum. You follow me? They'll give you every possibility, and you can do all Wentworth's problems in the back of his book. I'll give you the solutions if you don't have them. I think I've already put them up there. But you need to make sure you're thoroughly familiar with this stuff, because it's going to come back at you, and it's something you need to be familiar with generally as an engineer, because it's so common that we use this. Okay, I've said my piece about that. Now today, I mean, do you have any other questions about the quiz or anything like that, Homer? Okay. I don't have the average in front of me, but I know people did pretty well on it overall. So next, this is homework 5. And now we're going to get into stub tuning, or I'm sorry, into transients. And this is the section on transients that I told you about. So I gotta get my trusty document cam, see if it works. I didn't get to see the weather forecast for the Auburn area, but has that storm moved well inland or not? Anybody see it? Is anybody down by the Gulf at all? Anybody South Alabama? I don't think we have anybody. My other class, I got one person, I believe.
It looks like we get rain and thunderstorms through Wednesday.
Where's the center of that storm? I mean, is it outside? Is it out of Louisiana or not?
It looks like it's right on the border of Louisiana and Mississippi.
Okay. Let me tell you where we are. This is, what I'm about to show you is not going to be hard to understand. But I want to make sure I go through this, because believe it or not, there's little things that trip people up with this particular thing. So these are transients, and here's really what's going on. You're going to have a line here. It's going to have a certain source resistance here. And you're going to have some voltage here. Can you all see the screen okay, by the way? Everybody? I'm going to talk my way through it. And then I'm going to go through this. It's called a bounce diagram that we do. So when you throw that switch, as soon as it's closed, what that does is put a positive voltage right here, between here and here, the rails. And that's on the transmission line. Now that voltage, as soon as it's there, it will cause an electric field to exist between here and here. And literally a transient wave will propagate at the speed of light in that media. Now it's not always C. Remember, these things, transmission lines, have dielectrics. And the dielectric can be much larger than 1. So they actually propagate at a velocity which is equal to C divided by the square root of epsilon relative. And I'll talk more about that. Do y'all hear me on that one? Remember, don't always assume it's C, or else you get into trouble. Now, it propagates down when it hits, and I've got to tell you this. The instant you throw that switch, the actual impedance that this source voltage sees in series with this resistance is not anything to do with RL. The volt, or the value it sees here, is just Z naught. And he puts R naught here, but I would actually put Z naught because that is the common symbol for the characteristic impedance of a line. It's not R. So it travels down at the speed of light and hits here. Then a portion of that signal, just a portion of, which is a reflection coefficient at the load, times the incoming voltage, which would be V prime, is reflected back. So you get something like this. The voltage comes down to this point, hits this. Now the whole voltage has that initial V prime on it. Follow me? But now something's reflecting back that has gamma L, the reflection coefficient at the load, times V prime coming back at the speed of light in the media, or speed, the electromagnetic phase velocity in that medium, comes back and it hits here. Then it encounters another reflection coefficient. This one is the source reflection coefficient, and we get that by taking RS minus Z naught over RS plus Z naught. The battery looks like a short circuit because it's a voltage. And when you think about Thevenin analysis, do you remember how for Thevenin source, if you did a Thevenin equivalent source or anything like that, the way you get the actual resistance, Thevenin resistance or impedance was short the actual voltages. Do you remember that? And you open the current sources, short the voltages. That's the way it works. So you're going to see that reflection coefficient coming at the source side would be RS minus Z naught over RS plus Z naught. We'll get to that. Now that multiplies that wave that reflected back. So it would be gamma L V prime times now gamma source. And that one goes back, and you get the idea. I wanted to talk my way through it. Now this is how a bounce diagram works. And we're going to do, once you do several problems, you'll see how this works. First thing we do when we do a bounce diagram is calculate the time it takes for the wave to go from the beginning to the end. Make sense? And that's simply taking the distance, the length, whatever this length is, L, and dividing it by the speed of light in the media. So this, see how he has TL here? This is really equal to simply the length divided by the phase velocity in the media. That's all that is, TL. Can you all see that in your book? And here's how we do this. We start by saying, right, he calls this V0 right here. You can call that V0 if you want, but his V0 that you see how he has V0 there? That V0 is actually going to be equal to Vs times Z naught, and I'm using Z naught over RS plus Z naught. Everybody follow me on that? It's just voltage division. That comes down here, it hits here. Once it hits here, we draw this. We take the reflection coefficient at the load. Luckily, he shows this one clear right here. That's the reflection coefficient at the load. Now, I'm sorry he's using R naught, but just put in Z naught here. That should be Z naught. I don't like using R for anything but resistance values, not characteristic impedance values. I don't like that. So now you take that reflection coefficient times V naught, and you're just showing how this thing's bouncing. Here's time, and here's what's happening on the line. At any point in time, you can take a look that you have this voltage is already set up. This one's bouncing back. It hits, goes this way, this way, this way. Can you all get a feel for what's going on here? Give me a show of hands if you do. Pretty much so. You all see it? Now, how does this draw? How do you draw the thing on a bounce diagram? Well, keep your face, or keep looking at that. And what I'm going to do is just, or understand that, I'm going to move this off a little bit and then draw this.
Professor, I have a question.
Go ahead.
Why do we not factor the load resistance into the voltage divider?
Well, right here, you mean? Where the initial value?
Right, yeah.
Don't need that because this is the instant in time. Remember, there's no way this point, this voltage, just as that switch is thrown, can know anything about this load because the speed of light is involved in this, right? Right? And there's no way it knows that it's there. In other words, the only thing it feels is Z naught.
Okay.
All right. Remember, we're talking about times that have to do with the speed of light's limitations. So they're nanoseconds kind of things. Very short times.
Thank you.
Yeah. All right. Now, here's how you draw this up. Y'all see this right here? I'm going to show you how to draw it up. And I want to do it on a clean sheet right here. Hopefully you can see this. You come here and you put an axis. This is going to be time. And then start labeling points. And I like putting capital T. And capital T is just what he calls TL. And capital T, this is Wentworth's TL, is just the length of the line by really the velocity on the line, or C, divided by the square root of epsilon relative of the material and the dielectric of that line. So you put T and then 2T, 3T, 4T, 5T, 6T. And next, well, the first voltage we had on the line was V0, right? That was based on the initial voltage division, correct, class? It's going to stay in. Another thing I have to do is I have to pick the point on the line I want to talk about the voltage. So what I want to do here is I'm going to do the voltage right here at the beginning of the line, right here. So if I do the voltage right here, and I'm going to show you how to do the voltage at the end of the line at any point on that line. If I do the voltage here, you see initially it's V0, right? Now just keep watching. Stays V0, right? Until a pulse comes back and hits it. And it takes 2 time constants. Y'all follow me? If a time constant is T, is the length divided by velocity, it takes twice that. Now I want you to see that. So at least the voltage at the load, and I'll say that this is V at Z equals minus L, right there, is going to stay at V0, and it stays there until I hit 2T. Now, this is important. Now, you see at this point, see where it says 2T? 2 things happen simultaneously. I get this voltage, gamma L times V0, right? And I have to add to it gamma S times gamma L. These 2 come in, they're at that point simultaneously. Do you all see that, class? How many do? Right? So you have to put both of those values there. So you have to say now, whatever the change is, the value of the voltage here would be equal to 1, I'm factoring out the V0, plus, and then it's gamma L, but it's going to be gamma L times gamma S times V0. Please take a look at what I've done here. I'm saying at this point, I already have V0. That was started there. That's staying there. Now I have to add to it gamma L V0. That's the one that hit. And the one that's leaving is gamma S gamma L V0. You all see that? Class? So it would stay at this value here. How long will it stay there, class? Take a look. Until this point. Do you agree? Right? And that's 4 time constants, right? All right, so 4 time constants right over here. Now it's going to change. And what's the new value? And I don't know if it goes up or down. I really don't. It could go up. But the new value here will be the old value. So you're going to take all this. So you're going to have 1 plus gamma L plus gamma L times gamma S, right? Times V0 here. But now you have to add to it. Take a look at this. Gamma S, gamma L squared, right? Plus what? Well, the wave traveling out here would be gamma S squared times gamma L squared. So you're going to have plus gamma S times gamma squared times gamma L squared. Do you all see what I'm talking about? And you can see what's really happening is every time that I go 2 time constants, I have to add 2 terms. I have to add an incoming term that has some gamma S to the n plus times gamma L to the n plus 1. And you're going to have an outgoing one that's going to be gamma S times gamma L, both to the same even power, whatever that value would be, 2, 4, 6, 8. You'll see this. Agree, class? And you get this. Now, here's what happens to a bounce diagram in the limit. If you kept going forever, what you'd get is this. And I'll draw this for you right here. When you have a source resistance and you have V naught, or Vs, pardon me. Then you have a switch like this. Then you have your transmission line. As transmission line as a length L, characteristic impedance Z naught, and then you have RS. This is at Z equals minus L. The load's always at 0 unless there's some very good reason for not putting it there. You have to know the velocity on the line. So that would be the velocity. And in the limit, as t goes to infinity, what it looks like is this transmission line doesn't exist. It looks like this, that you have just Vs, you're going to have Rs, and then you'll have simply R load right here. And if you want the voltage right here, it's like the transmission line becomes 0. The voltage here at the load would just be equal to Vs times RL over RL plus RS. Do you all see that? That's what it'll go to in the limit, because in the limit, the transmission line appears to be infinitely short. If you think about, I hate to make too many analogies, but at the initial point where the switch is closed right here, this thing looks infinitely long. That's why it sees a characteristic impedance of Z naught. Even though it isn't, there's no way the information can be communicated from this point to this point after the switch is closed that the load is actually there, all right? That's just, it doesn't know. So it has to assume Z naught. And this bears out with a reality. But as time goes to infinity, after this wave's bouncing back and forth and everything settles, effectively the transmission line looks like a short circuit. And if you think about this, I'm trying to think of a way to explain this that would be a little better. If you think in the frequency domain, right? If we did a frequency domain analysis, well, we would be talking about omega. Omega is 2 pi f, and f is 1 over t. If you think of the times involved with the for the actual, the time it takes for it to go down the line, and that time, say 2 times that time, at that point, you can sort of make a fuzzy kind of analogy to a transmission line's impedance, where now the thing has some impedance. It's not just saying Z naught, it's something different if you were thinking about a transient analysis. But in the limit, as it becomes DC, where the frequency goes to 0, then the length of the line effectively becomes 0. I mean, because the wavelengths are infinite. If you think about wavelength being c over f, or velocity over f, when f goes to 0, the wavelength goes to infinity, doesn't it? This isn't a precise way, a great analogy, but I'm trying to give you some way of, in your mind, to think about it, or at least relate to it. That's a bounce diagram in a nutshell. Now, one thing about bounce diagrams, if you had a switch that turned down, shut, and then turned up, or basically shut and then opened, well, you could make that with you could add 2 different waveforms together. You could have a positive going wave, and then you could add to it at some delay a negative wave so that it would cancel the positive wave. We'll talk about that in a bit. There's ways of doing this. In other words, superposition does hold for this analysis. If you have a source, if you have the first source and the second source, if you find the solution to the first source and the solution to the second, you can add the 2 together to find the solution to the third for the voltages on the line. Understand? So those type of things do work here. This is a linear time invariant system, so they do work. Something else I'm going to tell you. Stay with me on this point here. This is a little bit tricky. All right, we did the voltage right here last time, right? Right on that edge. Now, what if I wanted the voltage at this point, right in the middle? Now, I want you to take a look at this. A lot of this will become clear to you as you're doing these problems. when I do any type of a voltage analysis, I always start at the upper point here, and I look at the voltage, and that, when I say look at the voltage, you have to look at where this line is, this crossing line is with respect to where you are here, if you're drawing in time. If I'm right at the middle of the transmission line, I want to see what the voltages look like. Take a look. I'm going to come down. It starts out at 0, right? At time 0. There's nothing at the center. The wave didn't get there yet. When I get to point A, that's, if it's halfway down the line, that would be as T over 2, correct? Now the voltage here would be V0, right? It would go up to V0. It would stay there until I came to point B, right? And then you would have to add to that voltage the reflection coefficient gamma L times V0. Do you all follow me on what I'm saying here? Now it would stay there until I hit point C. And at point C, I would have to add to it what? This is gamma L times V0. This is going to be gamma L gamma S times V0. So I'd have to have 1, if you think about it, I already have V0. Then I have gamma L, right, times V0. Then I have gamma L gamma S times V0, right? 3 terms. You can see through D what would happen as well. Do you all follow me? And this is something that keeps going and going and going. And eventually all these voltages, the voltage here, here, and the middle of the line, all go to the final voltage, which is just going to be V0 times RS, or I mean RL over RL plus RS. It'll always go to that voltage as it damps out. He's got some waveforms here. What he does is he shows you the beginnings of a waveform for a bounce diagram right here. He doesn't show you a lot. Up top, he shows you one, gives you a little better insight. And you can see as time goes by, the jumps or changes get smaller and smaller, and they're asymptotically going to go to a steady state value. When we do a few problems, it'll be easier to see this. Now look over here. This is something that, suppose I want this as my, what he wants to put is a small square pulse on for a short time. So he says, how do we do this problem right here? Where I've got, this is my pulse that I want to use to feed the transmission line. He creates it in an interesting way. He has VS right here in series with RS. At T equals 0, the switch closes. So that causes this first voltage wave to get sent and start ricocheting back and forth, right? And then at some T equals capital T, whatever that is, he shorts out the source. And then what you have to do in order to effectively do that is you add basically negative V0 right here, or you take and make minus VS here and turn that on. So here's what he's showing you. I'm not going to do this one now, but I think you can understand. When I look at the bounce diagram for just when VS is on and it's got to divide through RS, you all see how you get this first waveform here. It's just bouncing like this. You all see it, class? Now add to this minus V0, and you can see what happens is this. If you come here straight down, if you're looking at the center of the voltage at the center of the transmission line, halfway down to the end, you're going to see you get 0, then you get V0, it goes up to a value V0, and then when you add to it the minus V0, it goes to 0 right here. Do you all see that? Now, hang on for 1 second. Okay. And this is what he's showing you. Now it stays that way until what? Now you get the reflection from the wave here, which is V0 gamma L here. So this waveform would have a height of V0 gamma L, and it would have a duration that would be really the length of time T. From here to here, it would be the length of time capital T, which is just the width of that up here. Do you all see this, class? Bounce diagrams aren't hard to understand once you do a few, but I'll tell you, you have to do several before you appreciate it. So I'm going to make one up. I'll take one of his and just well, let's do this one on example 2.9. It's a good one. If we do this, what I want is the voltage at the load. Now, you'll notice when I want voltage at the load, what I really want is it's 0 until I hit T, but right here, it's not V naught. It's V naught times what? It's going to be 1 plus gamma L, because you see how the gamma L one is simultaneously there at the same time? So let's do the voltage at the end right there for this one. If y'all don't mind, everybody has a book, correct, class? Y'all have books there? Thumbs up somewhere. You got your book? All right. If you got your book, you can look at that problem. I don't need to draw it. What I don't want to do is look at the solution. I want to come up with the solution myself to that problem. And I want to get the voltage, let's see, at the end of the line. So what I want is this. I have 4 volts as my source voltage. This is going to be 25 ohms. Got a switch here at T equals 0. Here's my transmission line. And he's got Z naught equal to 75 ohms. And he has the velocity equal to C over 10, or 0.1 C. And then he has a load here of 125 ohms. This is RL. And the length of the line is 6 centimeters. By the way, this would be a transmission line associated with some sort of a, probably a chip. It's not a VLSI chip. This would be something, not a chip, would be like a board. There'd be either FR4 or Duroid. It's something, you know, something that was going to be small. We're going to mount a lot of stuff on before we insert it in some kind of, who knows, a cockpit maybe. When we have this, here's how we do this. Now I'm going to take you through it the whole way. First thing we have to do is find this voltage on the line. I'm going to call that V prime. I know he calls it V naught, but I usually call it V prime. And V prime is going to be the source voltage, right? Times what? You tell me. Anyone? You can unmute yourself, I believe. I feel like getting some interaction. John or Fowler, can you go ahead and tell me what I multiply that 4 by to get the initial voltage on the line? Can you unmute?
Coefficient?
Say again?
The reflection coefficient?
No, I want the voltage right here, just as the switch closes at T equals 0.
0.25?
I would do what? I would say 4 times what? I have to use voltage division, right? And it's not reflection coefficient. I would take Z naught, correct? Over 75, right? Plus 25. Do y'all agree with me there? Now, that's what? That's just voltage division, right? That's 75 ohms is being looked at as a voltage you're feeding with 25 ohms or source resistance. Y'all see it, class? Well, what is that going to be? Well, that's 3/4 of 4 or 3 volts, isn't it? Y'all see this, everyone? That's 3 volts. That's the initial voltage we need. Now we get 2 different values. The reflection coefficient. Don't look at your book now. Just the problem is drawn out. Try to work this and ask. If you don't understand something, ask. Next thing I need is the reflection coefficient at the load. What's that going to be? How do I always get reflection coefficient? I'm going to call on some people. Tyler, how do I get this?
It's ZL minus CS.
All right, it's ZL minus Z naught, really, isn't it?
Not ZL minus Z naught over ZL plus Z naught.
All right, so it's 125. It's always the impedance you're going into minus the impedance you came from, 75, right? Over 125 plus 75. You all agree with that? What's that going to be? Well, in the denominator, I have 200, right? In the numerator, I have what? 50, don't I, class? Do you agree with me? And that is going to be 1/4. Agreed? All right, that is gamma L. Now, what is gamma S? And remember, gamma S is going to be the reflection coefficient this way, right? So what's gamma S? It's the impedance I'm going into. I'm going to slow down here. I'm going to call on somebody else. John, can you see this? What would this be, the impedance? What would this gamma S be? And I'm looking.
I got 0.5, but it was negative.
It would be, well, tell me the numbers. It's 25 minus 75, right?
Right.
I'm going into 25. I'm coming from 75 over 25 plus 75. So that's minus what? 50? Agreed? Over 100. Agreed? Check my math. So that's simply minus 1/2, right? Y'all agree with that? I want to make sure everybody sees this. Now, I'm going to start doing the bounce diagram thing. And just give me 1 second. I'm going to see if I can. No matter what I do, I'm not going to get what I want. All right. Now what I do is this. I come down. Oh, I got to make one calculation. I have to calculate. I like to call this capital T, and it's the time constant. It's the length of time it takes for the wave to go down the line. And that's always going to be the length of the line, L, divided by the phase velocity on the line. Now for us, the length of the line is 6 centimeters, right? So it's 0.06 meters divided by the phase velocity, which is 1/10 the speed of light. That means it's 3 times 10 to the 7th. You agree with me, class? Speed of light is 3 times 10 to the 8th meters per second. A tenth would be 3 times 10 to the 7th. And that comes out, and I'm going to just look, he probably has it here, as 2 nanoseconds. So capital T is equal to 2 nanoseconds. You can look in the book, but that's correct, isn't it, class? All right. Now, what I do is this. I'm going to go ahead and demark. This is going to be 2 nanoseconds. This will be 4 nanoseconds, 6 nanoseconds, 8 nanoseconds, 10 nanoseconds. I'm using straight edge for this. Some of you probably don't need it. And what I do is draw lines like this. I do this because some people are really good with freehand drawing. I'm not. I'm only going to take it to 10 nanoseconds. All right. And this is the load, and this is really the entry to the line, or this is at the source end. With me, class? All right. The amount of voltage that's going this way, and you can put little arrows if you'd like, to show the direction. This voltage is just V naught, all right? And V naught happens to be 3 volts, doesn't it, class? Right here. We got the initial voltage, call it V prime. So that's 3 volts, right? Agreed? Now, the voltage going this way would be 3 volts times the reflection coefficient of the load. So this would be 3/4 of a volt going this way. You all see that, class? It would be the initial voltage times the reflection coefficient. Does everybody see that? Now, once it hits here, now that 3/4 is multiplying by the reflection coefficient to source, which is minus 1/2, right? So that's going to be minus 3/8 of a volt, right? And that's going this way. Y'all see this? Y'all with me so far? Give me a show of hands if you see what I'm doing. I mean, if I made a mistake, just let me know. You got me on this one? All right. What happens when I hit here? What do I have to multiply by?
1/4.
Right. And now it's getting small, right? Because now what am I going to have? Minus 3 over 32. Correct, class? Isn't that right? It's getting small in a hurry. What about here? What am I going to get? It's important you pay attention to this last one. I've got minus 3/32 coming in. What comes out this way?
3/64.
Positive though, right?
Right.
Important change is a sign change. So it's simply plus 3/64. And that's about as far as I need to go before I see the wave is effectively died down to a steady state case. Do y'all follow me on this? So let's chart that. I'm going to put this on a different sheet of paper, all right? When you do, after you do 1 or 2, it becomes very apparent to you. Now, first thing I'm going to do is say, well, where do I want the voltage? And I could have the voltage in the middle. I could have it at the beginning. I could have it at the load. It doesn't matter. Do you agree with me? What I want to do it as at the load, because it's the most natural place to want to know about a voltage is at the load. That's usually what you're interested in. So at the load right here, when I chart it, I'll do it right here. Call that time. And just do V at the load. V at Z equals 0, which is really V at the load of T. Well, that's the 0 point where the thing starts. It's nothing until, how long? This is 1 time constant. What would that be? 2 nanoseconds. Do you agree with me? Right. So this would be 2 nanoseconds. Then I might as well put in 2t, 4t, 6t, 8t. 2, this would be 4. I mean, sorry, this is 3. Pardon me. 4, 5. I know the only time it matters is when I'm going to go 2 time constants from there. But if you follow me on this, what's the voltage at the load from 0 to 2 nanoseconds, class? Anyone?
3 volts.
It's going to be 0, isn't it? 0 until you hit 2 nanoseconds, correct?
Oh, the load, yeah.
Right? If it's at the load, it's just 0. Then at the load, at 2 nanoseconds, what's the value? Anybody? Well, remember, at 2 nanoseconds, what's the unusual thing that happens? I mean, at the load. Don't we have an incoming wave and an outgoing wave simultaneously happening? So I have to have not just gamma L time, not just V naught here, but it's like right here when it hits, it's going to be V prime plus V prime times gamma load, right? Isn't it? So right at this point, it's going to go up to a value, and that would be V naught, or V prime, I call it, and it would be 1 plus gamma L. And for us, what would that be? Our gamma L was equal to 1/4, so it's going to be 1 plus 1/4, or 5/4 times 3 volts, right? So it's 15/4, whatever that is. Agreed, class? All right, now pay attention. And that's, what's that value actually? I don't even know what that comes out to be. Well,
3.75.
all right, 3.75 would be the plateau there. How long does it stay there for? Again, think about the bounce diagram that we did right here. Well, that's 1 time constant, right? That's 2 time constants. This would be 3 time constants, right? Or 3 times 2 nanoseconds, or 6 nanoseconds, right? The next point where there's a transition is at 6 nanoseconds. So if that's 2, this would be 4 nanoseconds. This would be 6 nanoseconds. At 6 nanoseconds, what happens? What do I add to this? Class? Can you all see right here? I already have this voltage, 3.75 on there. That stays there, it doesn't change. But I'm going to add something to it. What am I going to add to it, class?
-3/8 and -3/32.
Right, both of these two simultaneously. Do you all see that? So I'm going to add, and can you tell me what this is? It's going to go down a bit. This point is going to be actually 3.75, and then it's going to be -3/8, -3/32. I don't know what that is. Does Wentworth have it in the next page? I don't know if that's at the load or not. Anybody tell me?
Well, Professor, isn't it also, those are factors, so don't we have to multiply those times 3?
Well, wait 1 second. Let me hold on for 1 second.
No, those are, I think those are already multiplied times the voltage, so.
These, yeah, I made sure I multiplied it by I didn't put just gamma L. I put that times V naught. So my first voltage, like here, represents, that is the voltage on the line. This is the reflected voltage. This is the reflected voltage times this source coefficient as well. And these are actual things you just add up in numbers when you want the value.
Right, okay.
All right, so what does this come down to? Can somebody tell me?
3.28.
3.28? Okay. And you can see it's going to stay there for what? 2 round trips, right? So we're going to go from 6 nanoseconds, 8 to 10 nanoseconds, right? And at 10 nanoseconds, what happens? What do you get? That's down here. I didn't even get the one coming off, but you can see it's going to be small. It's going to be this times what? The reflection coefficient, which is 1/4. So this value is going to be 3/4 times 64. So that's 3/256, isn't it? Which is pretty darn small. Do y'all see that, class? That would be the reflected wave at 10 nanoseconds, correct? I don't mean to go too fast. How many see what I'm doing and understand it? Just thumbs up, show of hands, in some way indicate you understand. All right, okay, you got it, got it. All right, now, and I'm hoping you're all with me. At this point, I can say pretty much it's steady state. I mean, we're into the noise in terms of changes. You can take a look at what the value is, but by that time, It's going to go up a little, but you can see it's pretty much asymptotically going to the final voltage. And what will the final voltage be on this line? I told you how to get it. What do we do if we want the final voltage on the line?
Just make the transmission line just shorted, essentially.
Remove it and put the load right at the source, right here. And you can see I have 125 in series with 25. So that voltage would be what? 4 times 125 over 150, right? So the final voltage, V final, would be 4 times 125 over 150. And you can see what? 125 is 5 times 25. 150 is 6 times 25, right? So this is really 5, 6 times 4. Or really, it's going to be, what would you do there? That would be divide by 2, you have 10/3, right? And that would be the final voltage, which is 3.333333 volts. With me? That's where it's going to go to. Now, if I asked you a question, tell me this. Instead of having the voltage at the load, what would be the voltage halfway down the transmission line? So if I wanted the voltage at the middle of the transmission line versus time, and I wanted you to chart that, it would be this kind of deal, right? I'd start here, correct, class? And I'd start moving. Let's do this part right here. Y'all understand what I'm talking about right here? Hey, can one of you tell me how many students are in here right now? Because I can't see that on my end.
7.
All right, we're missing some people today. Is there any information that you have about the internet being out or anything like that anywhere in Alabama because of the storm? All right, I don't know what the problem is, but some people are missing. Anyway, we'll just keep going on this one. If we look at this in the middle, and I'm going to go here, and we're charting the voltage, what does it start at, class?
0.
Yeah, 0 until what? How long?
1 nanosecond.
All right, right. Half of the total time it takes to go to the end, right? Because it's so. If I was to chart this, and I wanted, I know it seems real simple once you see it, but believe me, I give these quizzes, and you'll be shocked at some of the answers I get to these things. So if this is time, and now I want the voltage at a length at really L over 2 down the line. I should say V of L over 2 versus time. So it's just down the line halfway. This is halfway down the line. Nothing until 1 nanosecond, right? And then what happens? What's the voltage? Anyone?
Three volts.
3 volts. Yeah, it's going to go to 3. And how long is it going to stay there? Look, that's 1 nanosecond, 2 nanoseconds, 3 nanoseconds. I have to add 3/4 to it, don't I? Right? I started with 3. Just think I'm coming down this way. That's 1 nanosecond. This 3 volt crosses that point. This indicates the 3 volts is at that point in time. Well, the point is at L is really it's equals minus L over 2, and at 1 nanoseconds when we get that jump of 3 volts. Now it stays at 3 volts until I hit what? 1, so that'd be 2, 3 nanoseconds, right? You all see this, class? Can you all see what I'm doing, guys? And at 3 nanoseconds, I have to add 3/4 to that, or 0.75. So then it goes to 3.375. So that's 1, 2 nanoseconds, 3 nanoseconds, and then it jumps up to 3.75 volts. And it stays there until what? Anybody?
Five nanoseconds.
Right, and at 5 nanoseconds, what happens? I have to add that, don't I? Or subtract that. I have to subtract 3/8 from that, correct? And what is that? I can't do that in my head.
3.375.
All right, so it goes down to 3.375, right? And it's going to stay there until when? 7 nanoseconds. Then I have to subtract 3/32, don't I? Class? Carlin, can you see this okay? Are you okay with that?
Yes, sir.
Yeah.
All right, and I mean, this should be obvious, but if it isn't, let me know so I can help. Is it obvious to everybody what's going on here? What we're doing? All right, when you add that, what number do you get? And this would be at 7 nanoseconds.
3.28.
All right, I'm going to leave it right there, 3.28. Just with a show of hands, how many get what's going on here? I'm not going to keep going on this if you see it. Now, remember, superposition applies. So if I wanted to make this voltage, and I want you to make sure you understand this, if, like Wentworth does this all the time, if this is time, he wants you to find out the response to the transmission line to this type of a source voltage where it goes to some V naught, and this would be T, that would be 0, this is time. It's just a pulse, right? Well, the easiest way to make this, if you want the truth, is to just say that my voltage V of t is equal to some V naught times U of t minus U of t minus capital T. That means you have some V naught U of t, and then minus some V naught U of t minus t. So what you do is do a bounce diagram for this, and then delay in time like he does by capital T, and have the same bounce diagram, only have negative coefficients for everything. What I'm saying is what he does here. If you take a look at this, here's his first bounce diagram, as if it was a battery. It was just energized. You see what I'm talking about? You all see this here in my book? This is on page 91. Now take that same exact diagram and shift it down by the delay T. So you've got the same exact bounce curve here. Now take these values, if it's whatever they are, if it's positive here, it becomes negative. If it's negative, it becomes positive, and just negate all the values on these lines. Do y'all follow me? Like here, it would be V naught times gamma L. Here, it would be minus V naught gamma L. This line here would have V naught gamma L gamma source. This line would have minus V naught gamma L gamma source. And then wherever you want the voltage, you put a line straight down from top to the bottom and start just going. When you hit this point in time, read off the value. Hit this point, read off the value, and add it to the initial value. Hit this point, add it to the initial value, and so forth. Do y'all see this, class? That's the way you do a problem like that, and it's straightforward. You can't mess it up. Where you can mess it up if you're not careful is right here, at either the load or the source, because sometimes people forget to add the incoming and outgoing wave simultaneously. Got me? You think you can handle this part? I'm going to give you some problems, and we'll talk about them on Wednesday. Now, I have a meeting right now from 9 to 9:30 typically, but I don't need to go there because I'm teaching. I'd rather not anyway. Now, I want to tell you, in the book, and if you have comments, by the way, for me about how the class is going, are you understanding the way I'm teaching right now? Everybody? I mean, and listen, I want to tell you, if you botched a few quizzes, don't be hard on yourself. Just make up your mind that you're going to focus, do the homework. If you keep up with the homework, that's one thing I stipulate. If you do it when it's assigned before the next class period, and ask questions if you don't understand something, you'll save yourself an enormous amount of grief. If you do that, you'll probably do well in this course. Where people get hammered are the people that cram. They wait until the test or they wait the night before the quiz and do everything, and they have a very short-lived memory. It's in and out in a heartbeat, and the final is comprehensive. And the final in this class, oftentimes in the final exams, you'll see huge differences in the grades. You'll get a lot of A's, I mean, a lot of very strong, and I mean, you'll get people literally at 5 out of 100 points. And so you get a lot of F's and a lot of A's. But if you want the truth, don't cram, keep up with this. Between every lecture, spend about 2 hours, 2 to 3 hours, maybe more, and then ask questions of me. And anytime you need me to answer a question, shoot me an email. And make sure you put in the subject line ELEC 3310 or something like that, because I have get so much email, I can't go through it all. I have to sort of, when I see a .edu address, I assume it's more important. Don't ever send me anything in Gmail or any other mail tool, because half the time they don't even let you see it. They put spam or junk or something like that, or phishing. And so I can't even see that stuff. Send it from your Auburn email account, and make sure in the subject, like ELEC 3310 or EMAG 1 or something like that, because then I can answer it. All right. I'm going to tell you, we're not going to do in Wentworth's book, he's going to do stuff where he talks about dispersion on the lines. I don't do that here. Dispersion is a concept in microwave you would do. It's not really, it's really when a wave starts spreading, and I'll just mention it so you get a little understand. He'll show you a wave being dispersed here. And when you have a nice square wave and you put it on a line, a voltage wave with square, and it's transient, what happens as it goes down the line, it starts broadening and it will start rounding the corners. The reason is this thing, a nice square wave, is made up, if you remember from signals and systems, you can take that and you can create a Fourier series where you have a whole bunch of different coefficients or weights times cosines, sines, or exponentials of different frequencies. And on a line, the velocity that waves travel on a transmission line is a function of the frequency. So different components of a square wave travel at different velocities, and a nice square wave, like he's showing right here, will all of a sudden start broadening. It'll go down in height, and that's caused by dispersion. You have to be aware of that when you're doing any kind of telecommunication work, because the line lengths become critical. You can't have a really long line with short pulses of signals, because they'll disperse into each other and you can't tell what's what. And that's more later on that. But now we're done with chapter 2, and I'm just about out of time, but we're into chapter 3. I want to tell you where we're going. In electrostatics, I'd like you to do this for Wednesday. I'm going to give you homework, but I want you to go ahead and read section 3.1 on vectors. Now, most of you know how to deal with vectors. Vectors have direction and magnitude. You know how to add them, subtract them. But then we're going to talk about Coulomb's law. You've had this already in physics, right? You've had the basic force law of two charged particles, Q1, Q2 over 4 pi epsilon r squared. You had that. Remember that in physics? That's basic electrostatics. We're going to start there. Then we're going to go into what is the E field. And we're going to go into the 3 coordinate systems, spherical, cylindrical, and Cartesian. And we're going to spend some time developing unit vectors and really talking about how we go about mathematically analyzing electromagnetics problems that involve static charges. And we'll be using the term voltage as well in the electric field. Any questions or anything for the good of the group before we go? All right. I'm going to put the homework up in a little bit, but I'm going to hop into this other meeting. Does anybody, if you have any other questions, just let me know. Nobody? All right. You understand today overall? All right. Good. I'm going to give you homework. Please do it. Let me know how it goes. All right. Talk to you in a bit. Take care, guys. Yeah. Did you have a question, Tyler?
No, thank you.
Okay. All right. Take care of yourself. Stay safe.